So just I want to give a recap of the previous lecture. It is second lecture. In the last class, we have developed some foundation, and we have seen that uh, any outcome of any, or you can say the product from the industry, is the outcome of handshaking between the multiple discipline. And also we have seen whenever the product has to be come out from the industry, any product come out from the industry, so the designing of the product is very important. In the case of designing, selection of material is very important, because at the end material has to serve the purpose. So selection of material is very crucial task. In the last lecture we have seen the material used for the different kind of application is the different, because the material has to be serve the purpose at the end of the day, because the material used for the aircraft is different the material used for the building a bridge, because the environment of both the material is different. Because if you see the aircraft is used, the surrounding environment for the aircraft is -40 to -50 degrees centigrade. So we have to select a material that can sustain such amount of force in such environment. But the material chosen for the, you can say, for the bridge used in Indian condition, where the temperature lies from 10 degree to 45 degree, so it has to be choose according to that requirement. And also we have seen that whenever any material is under threat, it has two responses. One response is called stress, another response is called strain. And in the case of material characterization, it is very important. Any material characterization has three important components. That components are stress and strain, and also the relation between stress and strain. And we have also seen that stress is something that can be experienced, and strain something that is can be visualized. Just like, see, if I am taking the example, if it is a just a cup, it is, if I apply the force over it, or I can say if any material is under any threat for the material may be the any kind of load. Suppose this, I am applying this load over this cup. So what thing you can visualize? You can only visualize the strain. Stress can't be visualized. Stress experienced by itself by the cup. Only we can visualize and measure are the basically strain. So that's why I'm saying the stress is the response, or we can say whenever the material is under any kind of load, it has two responses. One is called stress, another one is called strain. Stress can be experienced and strain can be visualized, just like I have shown the example. Because if we are, after the application of the force on this cup, we are able to observe the severe deformation. And what is this deformation? This deformation is called as the strain. And the stress is experienced by this cup. So it can't be visualized, it can't be measured. Only the thing that can be visualized and measured is called as a strain. And also we have seen in the last class, stress and strain are the point description. If I am asking a question, what is the stress in a body? What is the stress in any object? So the question is not posed correctly, because stress and strain are the point phenomena, right? So both are the point description. The question should be like this: what is the stress at a point? What is the strain at a point? Because both are the point description. We have also seen this in the last class, and also we have developed that basic concept about stress and strain in the last class, how the stress is experienced and how the strain we are able to measure. And also we are idealize a point, because generally we have studied about stress and strain, stress about the with respect to area. So we have also considering a point, and that point is idealized as a infinity small area. Generally we consider a point because we are interested to calculate stress at a point, but point does not has any dimension. So how we can calculating the area? So generally we are assuming that we are considering very infinitely small area, and we are idealizing that area as a point. So that's why stress and strain are the point description, right? So I am starting today lecture. In today lecture we will discuss what is stress and strain, and what are the relation between stress and strain, right? So stress is something that you can define simply. It is the internal resistance force developed in a body caused by deformation or against the deformation caused by the load. Simply I am saying stress is the internal resistance force developed against the deformation, developed at a point against the deformation caused by the load. That is called, simply called stress. So generally stress is defined load by area, internal resistance force per unit cross section area, and that internal resistance force is nothing else. You can say, if I considering any body like this, if I am considering any body, just a second. So if I am considering any body and that is subjected to the load like this, suppose this is the normal load acting over the bit. If I am considering any section, and if I am considering any section and the area of this section I am considering like this, A. So if I cut from here, so I will observe there are certain resistance offered by the internal forces, and the resultant of these internal forces, this R is representing the result. Suppose this is R1, R2, R3, R4, there are infinite force acting over it. If I am considering the resultant of this force, that is called R. And what is this R? This R is called internal resistance force. And this internal resistance force per unit cross section area is called stress. Normal stress generally we are talking about, right? So simply the stress can be defined, it is defined as a point, but we have idealized the point, or you can say the infinitely small area is a point. If we are defining in terms of infinitely small area, then we can consider delta A tends to 0, and the stress is nothing else, that is delta F by delta A. That is called stress. Because stress is the point description, it can't be defined over the area, but we assume that the area is very infinitely small area. Then we can consider the dimension as a area, or we can consider point as a area. We can idealize point as a area, right? And also we can see here, simply we can see that numerically generally we write, because we have to calculate the theoretically. So generally we kept this internal resistance force is equal to the external force. And what is this external force? That is acting over the body is P. So generally we write stress is nothing else, that is the P by A, and nothing wrong with this definition, right? So stress is nothing else, it is the internal resistance force per unit cross section area, right? And this internal resistance force we are considering, numerically we are considering internal resistance force is equal to the externally applied load, right? So simply we can define, and the unit of stress is simple, you can say the Newton per meter square. It is also known as the Pascal, and this Pascal is very small unit of the force, so very small unit of the stress. That's why generally it is represented in kilopascal, megapascal and gigapascal, right? So I hope stress is clear. After stress, we can see the type of stresses. So generally there are two types of stresses, direct or indirect stresses. Direct stresses means if we are applying force along the axis, so directly impact or directly we are able to calculate the stresses, that is called direct stresses. There are two types of stress we can understand. One is called direct stress. Another one is, these are the example of direct stress. Direct stress means if we are applying force along the axis, so directly the stress is produces. In case of normal stress, if we are applying force along the axis, normal to the axis or along the axis, the stress produced is called the normal stress. Directly, if we are applying parallel to the surface, so directly the stress produced is called as the shear stresses, right? So both are the direct stresses. Indirect stress is something just like if I am applying a load on the beam, if I am applying a TSL, just like you can say it is a transverse shear load. If I am applying a transverse shear load over the beam, what will happen? It will cause bending, right? So this bending and twisting, just like the bending stress and the torsional shear stress are not the direct stresses. These are the indirect stresses, because after the application of the force, directly not produces. Because when the TSL is acting over the body, there may be a possibility the normal, shear, both, and also the bending stresses produces, right? So these are the these stresses are called the indirect stresses. So the main focus is the direct stresses. Normal stress, if we are considering load normal to the surface, as already discussed. If I am considering any object and it is subjected a load like this, P and P, in that case the stress induced is called as the normal stress, because the load is acting normal to the surface. Or we can say, in the case of normal stress, load is always acting perpendicular to external load. Which area we have to consider? Perpendicular area, perpendicular to the external. This is the external load, and which area we have to consider? This area. And what is this area? This is the cross section area, right? So that's why the normal stress is represented internal resistance force, definitely, divided by cross section area. And this internal resistance force is nothing else, that is equal to the numerically external force upon area, cross section area, right? So generally normal stress is called as externally applied load P over cross section area, right? So how we calculate the normal stress? Normal stress we can calculate it external load by cross section area. Come to the shear stress. In case of shear stress, what happened? The load is acting tangential to the surface, right? How the tangential to the surface? Suppose if I am taking an example of rivet joint. If I am considering any rivet, rivet is like this. These are two plates fixed together with the help of a rivet, like this. It is a rivet, means we are interested to couple two plates simultaneously. So we apply a just rivet. If I am applying a force like this, so in that case, what will happen? The shearing action will take place. So due to that shear, what will happen? The stress will induce. That stress is called as the shear stress, right? So shear stress is nothing else. It is represented by tau. Normal stress is represented by sigma, right? So in case of shear stress, the load is tangential to the surface. In case of normal stress, the load is perpendicular to the surface or normal to the surface, as name indicated, right? So shear stress is nothing else, that is also internal resistance force. Generally in case of shear, what will happen? The tangential, when the tangential load acting over the body, there may be a possibility of angular deformation, right? Just like in case of normal stress, after the application of the force, there is a possibility of only dimension change, but in case of shear load or tangential load, what will happen? When the load is applied over the body, there is a possibility of angular deformation, shape change, right? To resist that shape, the stress induced is known as the shear stress, right? So that's why the shear stress is also represented load, external load, because numerically we always consider the external load is equal to internal resistance force offered by the material divided by area. Which area we have to consider here? We have to consider the surface area, correct? So we have to consider area which is the surface area, or we can say area which is parallel to the external load. Just like in case of normal load, which area we have to consider? Area which is perpendicular to the external load. But in case of shear, which area we have to consider? Area which is parallel to external load. Right? So in case of, if we compare both normal stress and shear stress, in case of normal stress, which area we have to consider? We have to consider area perpendicular to the external load. In case of shear stress, we have to consider area which is parallel to the external load. In case of normal stress, area is perpendicular to the external load, or in case of shear, parallel. Another thing, the load is normal to the body, and in this case, the load is tangential to the body, right? So another example we can consider of shear stress, because shear stress is very important and also sometimes it is very confusing. If we are taking an example of any, you can say just a second. If we are considering any example of just like a punch and die, sorry for that, I have to consider a pen. Okay. So if I am taking an example, suppose it is a die. These are the die and we have to cut a hole in a material. Suppose this is a plate capped over the die like this. The thickness of the plate is T and there is a punch like this. It is a punch. If I apply a force over it, suppose P is the force applied over it, right? After the application of the force, what will happen? This punch will go down. When this punch will go down, it will cut from the sheet. And when the cut from the sheet, the shape of the cutting sheet like this. It is called sledge. You can say this is a kind of sledge. So this is the thickness we have considered T and this is the sledge basically. So how this sledge come out from the sheet? By the shearing action, right? Which action taken place? Generally the shear action taken place between punch and sheet. Due to that, we are able to find out the sledge. It is the cutting part of this sheet which is required to us to define the area basically. So which area we have to consider in this case? The area we have to consider, suppose the diameter of the punch is D. So what is the area? Pi D into T. That will be the surface area of the punch. Surface area. Due to which, or we can say the shear stress is nothing else, that is the load acting, that is the tangential load P, and what is the area? Pi D T. So this way we are able to calculate the shear stress, right? And I hope this normal stress and shear stress is clear to all. Okay. Now the another thing is very important thing is types of normal stresses. It is also called as the axial stresses and bending stresses, right? Bending stresses is the type of normal stresses. So bending stress is nothing else, that is plus minus my z b, right? So this formula is basically the bending equation. We know the bending equation, sigma b upon y is equal to m upon I is equal to E by R. This is called bending equation, right? And this is the part of generally the normal stresses. Bending stress is produced by the TSL, generally transverse shear load. When the load is acting perpendicular to any surface, it has a tendency to produce the bending stresses, and these are the indirect stresses, right? So this is the proof of bend. We can also prove this bending equation, but proof is not the concern here. We are interested to know how much the bending stress induced in a material. This M is representing the basically the bending moment, the maximum bending moment a material can sustain without failure. And this ZV is very important factor. That ZV is known as the section modulus. This ZV is known as the section modulus. Suppose we have to consider the strongest section under the action of the bending. If which section is the strongest section, then we have to compare the Z of both the sections. Suppose there are two sections. One is the cross section of the one is rectangle and the cross section of the other is I section, and both are the made of same material. And we have to compare which one is the strongest section against the bending. The simple question is that there are two different sections. One is the shape of one is rectangular and the another one is the I section. And we have to check which one is the strongest section against bending. So which factor basically we have to compare? We have to compare the section modulus. Larger the value of section modulus, smaller the value of stress, and the smaller the value of stress means chances of failure will be less. So whenever we have to consider any section, shape of any section against the bending, so we have to consider section modulus. Any section which has the greatest section modulus has the ability against the bending, has offer more resistance against the bending, right? Similar way, axial stress is nothing else, that is the type of normal stress. Normal stress is also called direct stress. Why it is direct? Because whenever we are applying force to the material, directly the stress produced is called as the direct stress. It is also called the axial stress, because axial stress is also nothing else. If the load is acting along the axis, so we are also calling the axial stress, and also known as the average stress. So these are the different name of the normal stresses. Same way, shear stresses, and it is plus minus. I am writing this. If I am writing the normal stress, that is nothing else, that is the plus minus P by A. They may be tensile or compressing depending upon the type of external load acting over the body. Just like if the load is like this, under the action of the load, this load is tensile load. What kind of load is this? Tensile. Because this force has the tendency to pull the body. And this force has the tendency to pull the body. In that case, the stress induced is known as the tensile stress. If the bar is subjected a load pushing nature, means the compressive force, like this. If the force is compressive, the stress produced in that case is known as the compressive stress. Then the compressive stress will be minus P by A. Minus P by A. So that's why I am writing this plus minus sign, because these normal stresses may be tensile, may be compressive, depending upon the type of external load acting over the body. Okay. So further, shear stress, the extension of the shear stress is nothing else, shear stress, or you can also say the average stress, average shear stress. Another the component, another types of stress is torsional shear stress. Torsional shear stress, the similar way the bending stress is produced, the same way the torsional shear stress produces if the load is eccentric TSL, not acting along the axis, eccentric TSL. In case of eccentric TSL, the stress produces the shear stress, also the bending stress is there, also the twisting stress is there, torsional stress is there, right? So that's why this torsional stress is also important. What is the torsion equation? Just like the bending equation, torsion equation is also there. T is the torque, T by J is equal to tau by R is equal to G theta by L. This is called torsional equation. This equation is called the torsional equation. We are not going to prove this equation, just we have to understand. The similar way we can write the shear stress is nothing else, that is the T upon ZP, where this T is known as the torque acting over the shaft. Suppose any circular body, how much torque acting over the body. And this ZP is nothing else, again it is called polar section modulus. Polar modulus. Just like here, Z is known as the section modulus. Here in this case, this Z is known as the polar modulus. The simple significance is this: suppose one shaft is solid, another shaft is hollow, and we have to select which one is the strongest shaft against twisting, because when the shaft is rotating, so there is a possibility of twist and there is a possibility of failure. And if we have to choose, and there may be the different constraints, sometimes the space is a constraint, sometimes the weight is a constraint. So if we are according to the requirement, according to the specific requirement of the space, maybe due to the weight, if we want to compare between two shafts made of same material, one is solid, another one is hollow, which one is the strongest shaft against twisting? The important question is, which shaft is the strongest shaft against twisting? So we have to compare this ZP. Larger the value of ZP, smaller the value of shear stress. Smaller the value of stress means chances of failure is less. Chances of failure is less. And ZP is nothing else, that is the ratio of J upon R. What is this J? J is the polar moment of inertia, and this R is nothing else, that is the radius of the shaft. So basically we have to consider polar moment of inertia. Larger the value of polar moment of inertia, chances of failure of the shaft is less. And J can be simply calculated. It is a mathematical terms, everyone I hope know. Any for circular shaft, the value of J we can write pi by 4, or you can say pi by 64 into d ki power 4. This way we are able to know the polar modulus. Oh no, sorry. The value is not this one. Sorry for that. The value of J, because J is polar modulus. J is polar modulus, not the moment of inertia. Moment for any circular body, if there is any circular body and the diameter of the circular body is d, the moment of inertia means inertia about any of the diametral axis, either xx or y. What is the value of moment of inertia about x and y axis? The value is simply pi by 64 d ki power 4. If I am interested to calculate moment of inertia about z axis, which is perpendicular to the plane, that is called polar moment of inertia, that is called J, and the value is pi by 32 d ki power 4, capital D ki power 4, right? So this way we are able to calculate. I hope the type of stresses is clear to everyone. Thank you.